I need divine inspiration for this one. So we're reviewing. Your celebration is on Monday. Nobody has told me they have a conflict, or if you think you do or something. So it's the same. You can either do it in the afternoon or in the evening. You'll come to Zoom if you can all be early, and then I'll email it to you. And there was somebody in the evening group who wanted a slightly different time, and that is definitely negotiable. Just talk to me. It is buffers. This practice is good practice. So we'll go through it. I'll give you a chance to work on it. So buffers, titration. Again, that titration lab is due Friday, but if you need the weekend to get through it, it's just 1 point. As long as you get in by Monday, that you lose, and there's a way to make up that point on it, and that will give you really good practice with it. That's why I'm going to have office hours tomorrow, so those of you who want me to look at it and go over it with you. And then the second half of the test is the Ksp stuff, and then the question that everybody's wondering is about the complex ions, and it had to get squeezed in somewhere, so it really does go with the Ksp, Kf stuff. So there might be like one little question about it. And so that's why that stuff is due on Sunday. So, all right. And I'll go through the study set on Friday and post it so you can watch it and then turn that in. It won't be that bad. So let's do buffers. What is a buffer?
Something that prevents change.
Change in what?
In pH.
Yeah. So we're back to pH. We can do Ksp first. We're going to do the pH stuff first. So buffers resist change in pH. And Paul, to get the full thing, which is going to be our answers to 1, or how you answer 1 and 2, a buffer is made up of what? Do you remember what the 2 parts are? He's not sure. Somebody want to help him? Oh, go ahead.
Acid and a strong acid and a strong base.
No, that's exactly what it's not made up of. So actually, that is one of the keys. If you see a strong, the thing why he's getting confused, and that's actually a really good answer, so thank you, is whenever we see a strong, like down here or on the titrations, that's when we write a reaction and do a mice chart. So I did a mermaid mouse today in honor of both parts. So on this first question, where it says the ones that are buffers, my hand-eye coordination is fascinating. If you see a strong, it cannot be a buffer. And the reason it cannot be a buffer, since I like to ask explanation, is because strongs, this is a strong base and it's a one-way reaction. Buffers have to be able to find that balance point. And so they have to have both directions happening. That eliminates that first one. So if you see a strong HCl or NaOH is what our go-to is going to be for this, that is not going to work as a buffer. So B does work as a buffer. So with that, Paul, do you figure out what the answer is or not quite yet? You're still thinking. So it's not as strong. Does anybody want to help him? Go ahead, Major.
So weak acid and the conjugate base?
It's a weak with its conjugate. So if it's an acid, it's a weak acid with the conjugate base. You could also say it's a weak base with its conjugate acid. So D works also, because that is a weak base, and this is its conjugate acid. On A, we have the weak acid HF and its conjugate base. So yeah. Why does C not work?
There is no
There
acid.
isn't an acid.
Go ahead, Perry. What?
There isn't an acid.
Yes. There's no acid. Correct. All right. My handwriting's awesome. Keep meditating. By the way, I have absolutely loved everybody's papers on their meditation experience. So this one, they're both salts. There's no hydrogen. There's no acid. So that does not work. You have to have this whole weak conjugate thing because it has to be a two-way reaction between them to keep that balance point. All right, so number 2 is we're looking for the buffer for our blood. And so we look for, it's the explanation of why our answer is going to make sense, is we're looking for a pH that is around what? What are we looking for in these to figure out which one we want to choose? It's like a really simple question.
Exponent?
Yeah, the exponent. So our exponent that's going to be closest to the 7.4 is our middle one. However, you're not done because there is more to the question. We want to make the appropriate buffer, and as Major correctly answered on the previous one, a buffer is made up of 2 components. This has only 1 component. So what's going to be the other half of it? I heard mumbling, but I don't know if that was like God talking to me again. Christian, do you know the other half of it to get your point?
Would it be PO4, just HPO4 because
What's the charge?
-2 actually, sorry.
Yes, thank you. So 2 minus or -2. So this is my weak acid, and this was actually a tough question, so we got it. Because this is one of those amphiprotic, remember the frogs that can go either way, they can swim or go on land, but it is a Ka, so this is my weak acid, and this is its conjugate base. And the pH, a lot of you wrote the pH is around the exponent, which is great, that's fine. You could also say the pH is around the pKa. So sometimes I make it even easier for you by giving you the pKa. Questions with that? I also had this picture on there, and then this is fun to share. I'm very sad because it didn't print in color, but it's a sunflower, and I sponsored a little girl like 10 years ago, 12 years ago, to go to school in Nepal, one of the poorest countries in the world, and she just got a 4.0, like finished 8th or 10th grade or something. And so she's hoping to go into medicine, but that's really cool because that country is so devastated and has nothing. And so that was really fun. Checking my email last night, having no email from any of you, having that email. I love getting email. There was also actually a fun picture Major sent me from his birthday celebration. All right, so buffers. I give you a KB. You can solve with KB or Ka. Why does it not matter if it's a buffer?
You have both components, so it doesn't matter.
Yeah, was that Annalicia?
Yes.
Yeah, so since a buffer, in buffer problems, you always have the acid and the base. You can use Ka or Kb. So the piece you're solving for here, the ammonia is NH3. We run into ammonia a lot. That is the base. So remember, nitrogens are the base. That's what the Kb goes for. The ammonium chloride would be the conjugate acid, so NH4Cl. And if you use Kb, the conjugate acids are unknown, you would have to change your pH to your hydroxide. You can also change the Kb to the Ka. So Paul had made a comment once, you know, if you use Kb, it has an extra step at the end. Well, if you change Kb to Ka, then your extra steps at the beginning. But on these, you always have a choice. And then on this one, you're going to write reaction. So we're going to pause in a moment, but just to make sure we all do the correct reaction. What in my buffer is going to go on my reactant side to react with the NaOH?
The acid?
The acid. So NaOH is a base, and it is a one-way reaction because the NaOH is a strong base. So NH4Cl. So I'm going to pause us. If you're watching this later, pause and try these. can even try the ones at the bottom. You can even go on to titration. And so let's walk through the buffers. So on 3A, no balanced equation because there's no reaction yet. So your study sets are actually really good practice, that if you haven't done them, remember you have till Monday to get them in, and that's why you just lose a point. So definitely do them. And then on your worksheet, some of you have turned in worksheets. If you turned in a worksheet and you got like a 3 or lower, you can redo it and turn it in. You will lose a point for it being late, but you can always resubmit it give it till Monday. So we're just plugging straight into Ka or Kb, and let's do Kb just for the fun of it. State your formula. So here's the question: when does it matter that we have to use Ka or we have to use Kb?
During
Type-
titration,
During when in titration?
the equivalence point, when all you have left is the conjugate.
Yeah, so at either the initial or the equivalence, when it's an x squared problem, when you don't have the ratio. So at the equivalence point, you have to, and it's determined if it's only an acid that you're left with, you have to use Ka. If it's only a base. When you're in the buffer zone, which is this page, or in the pH between the initial and the titration equivalence point, it doesn't matter. Just as long as you state your formula, and that's part of why I have you always state these, that then we know. So this is hydroxide. So this is going to be 10 to the negative POH. So it's not the POH, it's 10 to the negative POH. So if my pH is 9.5, then 10 to the negative 4.5. And you can do it like this. You can just state above, hey, I'm plugging this in 10 to the negative POH. I like to keep it as this number, but you can figure out what that number is. I don't need to see all the little extra steps of pH plus POH equals 14. I think by this time we got there. I think it's really nice using color. So a number of you do use color, but identifying like I did, okay, this is my base, and ammonia we've used enough. So we're going to solve for X, and I have an answer key right here. My X should be around 0.142. It is moles per liter, because all the numbers we're plugging in, this is molarity. We'll talk about that other issue in a moment. This is of my conjugate acid. This is the NH4. Now, this is also when we have to do it as the whole thing, ammonium chloride. So whenever you're going to mass, you have to factor in the complete compound. So the chloride does matter, even though the chloride doesn't impact the pH. Right, so that's going to be, and let's keep 3 sig figs with the periodic table, or 4. That's factoring in the nitrogen, 4 hydrogens, and the chlorine. And then our volume, which you can show it. Oh, this was a comment for some people, or for all of you. This is always, when we solve for X, it's moles per liter. This is meaning moles per 1 liter. That's what molarity is. The volume will have to factor in over here to get rid of the liters. So 500 milliliters, you can just do the quick divide by 1,000 and just make it as liters. And that should give us around 3.81. A reminder, I've talked about it this whole week. You can go with the 3 sig fig rule, and that will work. Technically, the pH would limit us to 2 sig figs, but I would keep 3. All right. On this one, this has to be an acid. So this is the conjugate acid is reacting with our strong base. It's a one-way reaction. So we'll get NH3, and the hydrogen will go over to the water. and the sodium and the chloride will then combine. So the sodium is going to get knocked off. There's nowhere in NH3 for the sodium or the chloride. So you technically, actually, this is actually a good one to show. We've never had one where we see all three as our products. And we're doing the mice chart while your teacher gets to dress like this. All right. So M is, we're going to solve for, the key is the I is moles, because we're doing a limiting reactant. And so we have to get to moles. So the NaOH is easy. Those are the numbers here. We take 0.025 liters times 0.50 molar. Your chart must show units. And I would keep 3 sig figs in your chart. Zeros are not significant, they're placeholders. Even though my numbers technically only had 2, I would keep 3, because some of you are rounding to 2 here, like 0.013, and then your answers are going to vary too much. All right. Almost always the NaOH or the HCl is your limiting reactant. So if you're doing the celebration and it's coming out bigger and you can't figure out why, come on to Zoom and say, hey, can I go over this one? And you'll be the only one on there. And so you might have to hold up. I'm not going to say, hey, this is what the answer is, but I can help point you out where you might have gone astray. This step, there's a couple different ways we can do it. You can either take the molarity that you had there. You're going to factor in this volume. So you can do the 0.142 molar that we solved for the X times the 0.5 liters. You could also have done the grams and just gone grams to moles and ignore the volume. But why do we have to be in moles? Why are the mice charts? The whole point of the mice charts is you have to get to moles. There's 2 reasons.
Is it because it includes the volumes?
There is a volume change that's happening here. So that gets factored in. And the other reason has to do with it's actually a one-way reaction. So we're doing a limiting reactant problem. All right, what's wrong with my chart right now? Somebody must have it. At least one of you must have gotten it right. It's a buffer.
Have a 0.
There's no zeros in buffers. So no 0 in a buffer problem. Titration. So this is probably the most missed piece on this page, is that because you're going to do a big lab tomorrow, which is titration. And again, it's meant to give you practice, so you have that part down. And in titration, this is a 0. In buffers, it is not. So that's why I put them as 2 separate pages. I don't mix Ksps in with the titration, then a buffer and randomize it. It's going to flow just like this does. All right, so the NH3, we know from up here. The ammonium chloride and the NH3, they are mixed together. That's the point of a buffer. It has both pieces. So the NH3 is 0.25 molar times the 0.5 liters. It's the NaOH that was the different volume, and that gives us a number of 0.125. But it can help to put a line, or at least a line there. That side's different. This can never be your limiting reactant because it's not a reactant. It's product. So there's my limiting reactant is the NaOH. So that's what we're going to subtract from this side. From the reactant side, the other missed piece is you add it to the product side. So that's where a line can be helpful. So the NaOH has been effectively neutralized. We get numbers, so 0.0585 moles. The other piece that I keep emphasizing, it's really nice to label. This is my acid. It's the NH4. And then when I get over here, I have 0.1375 moles. That's my base. You can use Ka or Kb. But there's my acid and base. So if I was going to use Kb, the acid's on top, the base is on the bottom. If you use Kb, remember you're going to have hydroxide. If you use Ka, this number's on the bottom, that's on top. So you can use Ka or Kb. It doesn't matter. Either way, if you use Ka, your X is your hydronium. And that's why I keep saying, label that. If you use Kb, your X is your hydroxide. We're always going to go then to pH. So 9.63, 2 decimal places. You will be asked, like the worksheet was really good practice too, the worksheet 5. It's like a week ago, right? Why these answers make sense. So on A, we're looking for a pH around the pKa. Well, that one's grams, so that one I couldn't ask. But on this one, we added a strong base. So the pH should go up, and it did. But it should only be a small change because it's a buffer, and buffers resist change in pH. They maintain the pH. All right, questions. It's a nice thing. You can see you get to an answer, and that is why you're always giving your answers for pH to 2 decimal places. All right, number 4, this shows up on the lab. So let's walk through it. You have one similar. Hopefully it's not the exact same one. If it is, the key on these, we saw one like this before the first celebration, but now we've done more with titrations and stuff. You have to look at moles. And then you're also looking at strong and weak. So this is a weak base, NH3, and this is a strong acid. You have equal moles because the volume and the molarity are equal. So that's the piece I'm looking for. Which one do you have more moles of? If you have more moles, that one's going to win. We're keeping it simple. I mean, doing math, sometimes it doesn't, but we're just saying, so if they're equal moles, the strong wins. So the strong acid wins. Acids mean the pH is below 7 because they have equal moles. So the strong acid is strong, so it's going to pull the pH down. All right, on the next one, we have a weak base and a strong acid. But this time, the weak base, you have double the moles. And I'm not looking at my cheat sheet to do that. I can see the volumes are equal. If you have double the molarity, you have double the moles. It's the moles that matter. It was the point of the mice chart. The other thing I never realized until Zoom was I get to dress up like a mouse. So you double the moles. This is why we can't wear masks going back to teach, because it just wouldn't, I'd have to find like so many masks then, wouldn't I? So double the moles, so it's a base. The pH is above 7. It's like this pH is too low, this pH is too high, and this one's just right. All right, so strong acid, strong base. Again, there are 6 strong acids, 6, there's actually more than 6 of each, but we're going to keep it as HCl, NeOH, so you get the big point. But if you take, you can see this is double the, this is double the molarity, this is double the volume, so they have equal moles. This is the only way we're going to come out right at 7. Equal moles of a strong acid, strong base. This is where the Goldilocks is happy. The pH is 7. And then you add 25.1 milliliters and it's off. But that's what I mean by let's do this without doing calculations. I don't need a whole bunch of calculations. All right, I wrote a quick note to myself to remind you all. So we're actually at the end of week 3. 2 weeks from now, we are done. It moves fast in the summer. And so I kind of analyze it like it's my silent meditation retreat. We're in the heart of this. And so the first week is kind of like the glorious week. You're at the beginning, and the end we're in the home stretch. You can see the end. We're in that middle part where sometimes, right? And so this weekend, this heat wave is probably good luck for us because you're going to stay in and do your homework. Come to office hours. Don't be shy. Especially if there's a lot of people, don't be shy. And if my office hours aren't working, you got to communicate with me beforehand, like today, and we can negotiate. Like on Saturday sometime, I could possibly meet with you briefly. But you guys want to be looking into a demo idea this weekend and communicating with me. We do have a week to come up with something, but next weekend you're going to be wanting to put your demo together and stuff. So especially if you're going like have big plans for next weekend, you want to figure this out this weekend. Having ideas, something will spark an interest. So, all right, let's look at titrations. All right, so we know we have a reaction because we see the strong, and the other piece that's reacting here is our acid. I gave you the Ka. I should be giving you Kas and Ksps and stuff and Kbs on there so that we all have the same number. Yeah. So you need to do your reaction. We'll do that together and then I'll give you a chance to work it through. Plus the NaOH. It is a one-way reaction. This is the hydrogen that comes off. So C6H5CO2, it lost the hydrogen, and so the hydrogen is replaced by the sodium. Again, you can show the sodium first or last, and then the hydrogen goes with the hydroxide, so water, which we kind of ignore. Mice chart. So I don't give you a lot of information because the key is once we find our moles, the moles of the two reactants are equal at equivalence. So I give you enough information to find one of the moles, and then you can find the other one. In this case, I give you grams, so you just go straight to moles. There is one other piece, though. We're not going to need the whole mice chart. You will need to figure out your volumes. So I gave you the volume of the C6H5CO2, which was 60 milliliters. We had to figure out the volume of the NaOH. So on your worksheet, the titration worksheet, I usually have a separate thing there, but realize that you should be hitting my answer right on the money. So 8.48 or 8.47, we're slightly off. So somewhere in there, and then see if you can fill in the chart. So play with it, and then here we're going to be, this must be past the equivalence point. Yeah, because we're getting a higher pH. So I'll pause again. You can take a 5-minute break, or you can try whichever one you want. Before we take a break, so I put somebody else on the board. By the way, was that Peter who answered my question like half hour ago? I think it was. I don't even remember.
What about when you use x squared?
Yeah, that was you, Peter, right?
That was Peter,
Okay.
yeah, that's me.
My question is, what is the one piece of information you need from A to do C? Anybody?
The moles of the acid.
Yes, I heard Max, and then I think Paul, you're like in harmony. Paul, you're already up there. But yeah, so here the moles, this number is going to be the same number down here. The NaOH is a new number, so this volume only holds true for this question here. So try it, try something, try whichever one you want, and so you can keep going if you're getting it and you got that moles. So just a reminder, if I give you grams, then all you're doing is taking your grams of the full compound, the C6H5CO2H, and we go to moles. It's one step. we do not factor in the volume. We're just changing grams to moles. That's our moles. Only at equivalence, these are going to be the same moles. So it's the perfect stoichiometry. It's what all of 221 and 222 assume. We just now look at reality. And so the reactants cancel each other out and we're at the product, which is the conjugate base, right? So back to the question I'd asked earlier, which Peter answered correctly, at equivalence, and it clearly will tell you you are at the equivalence point. You're at that perfect point. That is where you have to switch to the conjugate. And so we started with an acid of Ka. We have to make the switch from Ka to Kb. And somewhere you want to state your formula. Doing Kb. So conjugate acid hydroxide over the base. And that's our base. It is x squared. And the other key is we need moles per liter. So we have to find the total volume. Yeah, so we're going to have moles. You can figure out what this is, but this number is going to be the total volume. And this is where on the worksheet, I had you do it as a separate step. We know the 60 milliliters. To find the volume of the NaOH, we take the moles and we divide by the NaOH's molarity, the 0.2085 molar, which is moles per liter. So the moles will cancel and the liters will flip to the top, and you will get 0.0265 liters added to the 0.06. This is 0.0865. I didn't actually punch in what my molarity was there, and you can put it in like that. Your X, it is a base, is your hydroxide. Label that, because then that will be your answer down here, our X. So the X is 3.2 e to -6. All these numbers are molarity. And then the negative log of the X up here will give you the POH, and then you change it to pH. It is a conjugate base, so the pH is above 7. Because only conjugate base is present now. I mean, only is not a true only, because there's always an equilibrium. There's always, it's at equivalence. That's the only time I'm going to have you do the chart. There's X squared. Which other number gets the X? I'm sorry, what other compound gets the X in our chart? It's different every time, depending if you have a Ka or Kb. X squared is the numerator. So it's the hydroxide and the conjugate acid. This was my conjugate acid. Even though I started with it, at the equivalence, you change your perspective. It's really good to change your perspective. So Damon gave me a really good meditation in his meditation thing. And it is, since we're still like right after the new moon, the skies are like amazingly crystal clear. Go out at night and just lay down and stare at the sky. And then change your perspective, that instead of looking up, that you're looking down at the sky and see what happens. It's really fun. Sky's pretty amazing right now. So if you see a shooting star, it takes on a different meaning then, right? The meteor shower should be in its height, or it was, or it is right around now. All right, so these two, it's whatever was in our numerator, which is our conjugate acid. All right, our denominator here, this is my base, so that's this number, which I did apparently figure out, 0.0639. That has a negative, so the sodium was coupled with it. So these are going to be the same number, 0.0639. So it's basically all the moles are sodium. All right, and we have one more, and it's the easiest one to find. hydronium. Hydronium, you can just always do 10 to negative pH. Now, sometimes the hydronium will be your X value if we're using Ka, but here we just do 10 to negative pH and you'll get a number. You actually find that number. I'm okay with you writing whatever it would be, 10 to negative 8.5. Questions, equivalence, the chart. You should all be feeling comfortable. This is the point of that lab, is to give you practice. So then you just need to practice your KSPs and your buffers, and you should be good to go for this. All right. The other thing is, don't be lazy. You guys are getting a gift. You get 3 hours. So show your work beautifully, which you have all been doing. So the reaction's still the same reaction. It's up to you again if you want to show the water or not. That shows a lot about your personality. And we want to say our mice chart, that one piece that is still the same is the 0.00553 moles. That when you do the lab, there's 3 different titrations in there. All right, the moles are no longer equal. So the NaOH, we have a new volume, 0.033. And this is its molarity. So don't rush, but do mind the time. And we get a new moles, so 0.0. And the other thing, and it was a really wonderful question somebody had asked me, and it had to do with numbers. And this wasn't actually what their question was. It is something that I see every year. It's the zeros. So just be careful that you show your place value correctly. This is now my limiting reactant. We are past the equivalence. Post equivalence or past the equivalence. This is the oops. You went too far. We also know that because if you really did all your math right, this volume was less than this volume, the 33. Here we're at 26.5. So we're going to subtract the 0.00553. The conjugate base can never get above 0.00553 moles. You can ponder that. We do have to subtract on this problem. So 0.00135 moles. And then we went to labels. So this is our conjugate base, which means it's weak. Which means we go back and use our KB that we figured out up here. This is a strong base. This is the NaOH. We can go straight into POH equals negative log. However, what's my however?
It needs to be a molarity.
It needs to be molarity. So we need total volume. So again, and it sounds like you've got this down. The lab gives you really good practice with it. So we kind of have yesterday and today all this KSP stuff that we're doing, and then the lab. And so I have it due Friday because I was trying to respect letting you have weekends off. But if you turn it in Monday, you lose 1 point. So if it's gonna be hot tomorrow, just do it tomorrow. So the total volume, this one's easy. So you have 33 milliliters here at this point. So it can be nice. We actually, one year, we'd always have mice V. We always had a volume row. The volume from up here that I want is the 60 mils. That was the original volume that we're adding dropwise the NaOH to. This 26.5, the NaOH volume is only true at that point. So this must be what, 0.093 liters. And we would plug in, remember this is your POH, and then you just change it. I don't need to see the step. You tell me what your POH is, And then underneath, you can just say, okay, it's my pH. And it makes sense when I ask you, because you have excess of a strong base. It's a strong base, so the pH should be really high. Here, we have the conjugate base, but it's weak. So our pH, it's above 7, but it's not super duper high, which is 11, 12. All right, half equivalence. What's the trick?
I got a question. Do we do anything
ahead.
with the number of the conjugate base? Do we do anything with that number?
No, so thank you again. So this number for the conjugate base, why do we ignore?
It's because it's past the equivalent, right?
Past the equivalent point, it's because it is weak. You would have to go into the KB like we did here. You would solve for the hydroxide, which is going to be a number like this, 3.2 e to the negative 6, which is much smaller than this number. I didn't punch this number in. So if you want to do it, you would go through, you would get a number like this one. It's going to be slightly different because the volume is slightly different. So this would now be 0.093, but it'd be pretty much the same. That X you would add to this molarity, and then you can find the POH. And so it might end up as 12.17. So it's not worth it, is basically what the answer is. So it's a great question, Major. And the answer is it's because it's weak. It's contributing a very, very small amount of hydroxide compared to a strong. Because a weak has that whole equilibrium. Yeah. Half equivalence, what's the trick? pH equals, I never give you much room on this because it's
pKa?
pKa. Is that Perry again?
Yeah.
Hooray. So pH equals pKa. So we just do negative log of your Ka. Oh. Sorry, I laugh because that's like supposed to be one of those things, right? That a warrior or a monk that you learn humility, and having to videotape yourself while you're doing math. There's nothing more fun. All right, titration curve. So we've done these. There are some things that some of you are leaving out. So you are going to be drawing one on your lab. On the lab, it's a weak base. So I'll do a quick sketch just to remind you. This is a weak acid. So the idea, this is like always a rough, you have that sloping area, and then it does go pretty much straight up, and then it's roughly flat. I mean, these are over exaggerations, but that's our idea. So it's not like this gradual walk in the park. We do need to label. In this case, we're only going to label, well, we have 3 points. So your equivalence point, it's not smack in the middle of this up down, but it can be. I don't really care. It is in the cliff. This is pH over here. So what do we find? 8.5. And again, if your pH is slightly off, it's almost always the volume. But hopefully today. And then we know our volume here, which was, this is the volume of whatever you're adding. So volume of the NaOH, not the total volume. We're ignoring the 60 milliliters or else it makes it harder to do actually, which was 26.5 milliliters. So that point, and you should do your ... Colors is wonderful. All right, show our dot. We can do the half equivalence. Half equivalence means you're halfway there. You're at half the volume, not half the pH, half the volume. So this will be 13.25. This is our half equivalence. This is whatever D. So it does come out as half the pH. That is totally coincidental on this one. It just has to do with the Ka value I happen to have picked. So 4.20. The other numbers here, the initial pH, this was probably the most missed piece on the worksheet. On the worksheet, I didn't have you find the initial pH. There was somebody who figured it out, but we don't know what it is. It's probably in the range of of 2 to 3, 2 to 4. It's not going to be 0, but it is lower. On the worksheet, and it's worth looking back at that first pH that was like 7.11, that was at like 9.99 milliliters. And a lot of you put it at the beginning. And so you want to be careful of that. All right, we do have one more, which is up here. And that was our 12.16. And that was actually, sometimes it's like right after, sometimes it's like at 27 milliliters. It's really one drop that you're suddenly up there. So we're here, and this was our volume. Here we did 33 milliliters. So sometimes it's right next door, and it doesn't matter. This is pretty much flat. This is excess of our strong base. This is where the conjugate base only is present. And then this is that buffer zone that we talked about. It's a ratio of the conjugate base and the acid. The weak acid are present. So I am looking that you guys can get your points in there correctly. It's different on every one. All right, I did ask, we did go over this one in our notes. So a strong acid would be, you can go back and look at the notes when we did that, because I drew it out in detail. And it might be worth it to go back, and you don't have to rewatch all the lectures. Although last year, the people who really aced it, they just put the time in. Because now those, when I drew the titration curve, it will make sense. But the HCl, we start lower because it's a strong acid. And since it's strong, it's flat. It doesn't have this nice slope going up. The equivalence looks similar. So we're starting lower. The other thing is, and it goes back to this question. If you have a strong and a strong, equal moles, that's in a titration, that's the equivalence point. So at the equivalence point of a strong and a strong, you would be at a 7. The one on your lab is the opposite. You're going to be doing a weak base, and the curve you're going to be drawing. So you're going to have initially a slope, and then it drops down, and then it flattens out. So we did one somewhere. Any questions? Buffers, titrations. And again, the lab gives you practice. First page is a weak acid and a strong base like this, and like your worksheet. And then the next 2 pages are the weak base with the strong acid, so going the other direction. And then don't forget to go back and practice buffers. Key with buffers, you don't have a 0. You do have a number there. So, but you can see pretty much. All right. We're gonna move on to KSPs. So, what is the key to all the KSP questions? And again, it's going to be organized like this. You're going to have the buffers, then the titrations, and then the KSP stuff. And then probably one complex ion question. Major, we're going to answer my question. What's the key to these?
Yeah, just write the equation and the Ksp expression first.
Right. So let me just make sure everybody's got it. So for this one, calcium hydroxide. And then we'll take a break so you can try it or take a break. Always solid to aqueous. You must show your charges of your ions. So sometimes I get lazy looking at the worksheets and I don't look at everyone carefully. Usually on your exam I do, so just be careful. And write your KSP expression. A couple of key words that will help you. Like when it says saturated, I don't give you any math, I'm just like solve for it, but I give you a pH, which you can find hydroxide. Some questions that came up during office hours, which were really good questions. And again, the study sets are really good practice. Totally respect those of you who are like, I'm going to do the study sets over the weekend, because I would rather have you lose that point and really focus on the study set than rushing and trying to get it in and like having sloppy work and stuff. Same with the worksheets. Worksheets always have a bonus. So the question though, and it was a really awesome question, a couple people asked it, is how do I know what ions to cross out? And so Nick, nitrate, you see nitrate, you're going to cross it out. So that leaves me with the PB. PB is a cation. So as long as you can cross one of them out, then in the other piece, cation has to be with the anion. So the PB must be with the Cl. Hydrogens, acids are soluble. So the hydrogen is the piece. Now, if we're starting with grams, you do need the full compound. But so that's where we're going to find the PB and the Cl. So like down here, right? Sodiums are the other ones we're crossing out, and the nitrates. However, I'm wanting you to go to grams, so you will have to factor in the whole sodium. But for your precipitate, it must be silver sulfate. And so since I gave you Ksps, you're not going to have to go look them up. But that's our idea. You can pick whichever ones you want to work on, or you can take a break. This is some of those double equilibrium ones. All right, I'm going to pause this. So again, the key to these are write your equation, state your Ksp, take a deep breath, and smile. All right, if it's a hydroxide, so this is like on worksheet 7, the one from yesterday, you had it was, I think, though, magnesium hydroxide. So there was, the question also gave extra information, which was the mass. The mass is not important. What dissolves is important. So that was the key. I wrote at the top of the study set. Ksp tells us how much dissolves, how soluble, because it's looking at the aqueous. That goes back to the first lecture about we don't include solids. The solid is there, it just doesn't matter how much. What matters is how much dissolved. It does something I left out in the notes yesterday. pH does influence Ksp. I'm sorry, solubility. Ksp is a constant. Temperature will change K. We've done that before. There was a question yesterday on your worksheet. So 10 to negative POH will be my hydroxide. So 10 to negative 1.6. All right, so changing your pH, 14 minus the pH. The calcium is half the hydroxide. So normally we do the hydroxide is double, but since we know the hydroxide, so this, I didn't punch the number in. I just do it like this, divided by 2. Biggest thing is you have to remember to square the hydroxide. So we're not doubling the hydroxide because the POH is giving us the hydroxide. Right, that was solved for our Ksp, and that's where we get that number. Ksps are always going to be small. They're always less than 1. They're always reactant favored. They want to form precipitate. So since I have space, I'm going to deviate for a moment. There was in our notes back on page 35, so you can kind of make a note there, but it's page 35 in the notes. I forgot to go back because I had offered a bonus point and nobody's emailed me about that nickel hydroxide question I talked about. pH does affect solubility. Obviously here it will, because it will change the hydroxide, but it does affect others. So like in this case, if we increase the pH, that means we're increasing the hydroxide, right? Higher pH means we're increasing the hydroxide. So if you have more hydroxide, in this case, it's going to shift in the reverse and you'll get more precipitate. So it's going to be more precipitate means less soluble. There's less ions. Typically, solubility, if you increase the pH, typically it does, even if there's not a hydroxide. And it has to do with most of the ions that we're dealing with. I'm trying to find one on here, sorry. Really? I didn't pick one on here, the whole thing. Most ions that we deal with are weak bases. So like here, calcium fluoride. The fluoride is affected by pH. So higher pH typically makes them less soluble. The exception to that, and that's why I was having trouble finding it, is number 7. And it has to do with that we have a chloride. So the conjugates, keep it up here. If the anion is a weak base, then increasing the pH, this is going to hold true, which means that if you decrease the pH, you're going to make it more soluble. So what's going to happen typically if you decrease the pH, you're going to help to decrease. So here, if we decrease the pH, we would decrease the hydroxide, or you're going to decrease your weak base. The exception to that is the conjugates. This is a conjugate base of a strong acid that has no impact by pH. So pH has no impact. So that was the HCl, the HI, and the HBr, all those. So that was this question's at the top of the page. This one, which salts become at low pH? The hydroxides, the Kf. This would not, and this would not, because they're conjugates of a strong acid. That shows up on the study set today, so I'll be talking about it, but not everybody. I do recommend going back and you can listen to when I go through the study set, because I talk about a lot of stuff. All right, we have to figure out our precipitate. It's never the nitrate. Hydrogen's also, but the PB then would combine with the chlorine, and it is PbCl2. That 2 there was from the nitrate. It's going to go with the chlorine. So we have a solid 2 Pb and chloride. And state your Ksp. So the biggest question that I have been asked in the past 24 hours, when do you double and when do you not? Like here I have 2, do you double? This one you do not. Why?
Because there's some information given, and if there's no information, I'll double.
We're mixing 2 things here. We're mixing lead nitrate and HCl. When you would double is on number 6, because all we had was calcium hydroxide, or in this case, I had to do the stoichiometric ratio. So the 1/2 was the stoichiometry, that there's 2 hydroxides per 1 calcium. Yeah, like here on number 9, we're not going to do any kind of doubling because we're getting it from 2 different places, sodium sulfate and silver nitrate. All right. So the PB is that M, that little m is millimolar. You guys were here yesterday, so you probably got that. So it's 3.8 e to -3 is milli. And so that gives me my molarity. but this is where our volume changes. This was the question, shows up on the worksheet today too. If your volume changes, you have to factor that in. So you're doing basically M1, V1. You don't have to state this formula, but M2, V2. And so we're dividing by our final volume. So the initial volume for the PB is, you can do it in milliliters or liters, because we're going to cancel out the volume, and it's the total volume. The final volume is 200 plus 300, so 500 mils. So they just have to be the same unit. That's my PB. My chloride, milli again is 4.1 e to negative 3 molar, and this is 300 milliliters over 500. The most missed thing on this, you have to square that chloride. You have to square that. That's where I get, this is a Q problem, because it doesn't say how much forms, it says will a precipitate form. All right, so you solve for Q, you get my answer, hopefully, if you don't. And then we compare K and Q. If you put them alphabetical, K was 1.3 e to negative 8. Q is 9.2 e to negative 9. They're negative exponents. K is bigger. So explanation, this is all I'm looking for. If you put it alphabetically, it points you in the direction. So you're not there frantically having to look through your notes. Having your notes handy will be fine. All right. And the students who really studied, they did this test in 2 hours. You get the 3-hour window. That means no precipitate. It is going forward, and if it goes back, you get a precipitate. All right, on this one, we're comparing 3 different things. On the worksheet, you had one like this, and on the study set yesterday, we had one like this. The question, there's 2 different ways to ask the question, so just be careful. I'm wanting to know which precipitates. So either way, you're solving for X. On the one on the worksheet, I gave you a concentration of the cations. So you did have to plug in, you weren't actually solving for X squared, you're doing 0.1 times the X. So just be careful if I give you a concentration, but this one I didn't, so you're solving for X squared. On this one, there's 3 ions, so it's going to be 4x cubed. And this one, it's just X and X. So Ksp equals X squared. So you solve for X. X is always the solubility. So the smallest X is the least soluble. And so that will precipitate first. That's all I'm looking for. You would give me your X values, and sorry, drop this. Right. I don't actually have my numbers figured out. Apparently this one's going to be the first to precipitate. Did I give the order? I did not.
You did.
Did I?
Yeah.
Oh, I did. All right. So 1, 2, 3. I don't know where my answer with all the numbers are. All right. The next one. Again, you have 2 pieces you're mixing. So it's a really great question that came up at the beginning of office hours. And the key is, I didn't give the answer like this is what it is, as you have to go through them. You're crossing out nitrates, you're crossing out sodiums. It's really, I'm not going to start throwing like snowball ones at you. I could. Silver likes to be a +1. That's why here it's a 1-to-1. But if you notice, there's 2 sodiums, so there's going to have to be 2 silvers there, Ag2SO4. And I can't control. You can go on Google and say, hey, what's the formula for sulfate? I used to major, and Devin actually, oh, really? I don't have one. There's certain ions that show up a lot. And so if you want like a little list of them, so you're not having to Google, sulfate, this is sulfate, carbonate. So having a little card with them in chem, I know you can get like these nice lists and people go, Dr. Russell will have a list and they're huge lists, but really when we were real and people just learned them, nitrate just keeps showing up. I personally like a much simpler list because these are phosphate is the other big one. And then keep in mind, right, the first column on the periodic table, these guys are our +1s, these are our +2s, and then in the middle, we kind of have to figure it out. But those 4 show up a lot. There's a couple of other ones, but you can, right. Silver likes to be a 1. So this is our silver number, 0.022. And sulfate, we don't know. So it's just X. State your Ksp equation. And I gave you a Ksp. The silver is squared, but we don't double it because again, the silver and the sulfate are coming from different sources times the sulfate. So the 0.022 will get squared times X, and you plug in the Ksp, you find X. I didn't solve for all of these. I'd have to find my answer key. That will be your moles per liter of your SO4. Because that's what my X is. Now we want to do a mole to mole ratio. And it is 1 mole of sulfate. And the mistake that several of you are making, you went to silver sulfate. That's not what my question asked for. So once you get X, take a deep breath. It's good to breathe. I want sodium sulfate. So we're doing, there's only 1 sulfate in sodium sulfate. And then you can go to grams of sodium sulfate. We do need to get rid of the volume. So our volume, I gave you here 250 milliliters. You will be multiplying by the 0.25 liters. Right. Again, this is always moles in 1 liter. So the number there, the volume you'll have to multiply by to cancel them. Questions on that page 3. All right. Simultaneous equilibrium. So we're going to write our half reactions. We'll start with the zinc hydroxide. So just start with your solid. And it breaks into its ions. Is that Ksp or is that the opposite? It's solid to aqueous. So this is the regular Ksp. It's the number I gave you. The second one, the zinc cyanide, that is the one that is flipped. So this one is flipped. So we have to do 1 over its Ksp. And then we multiply to get the K net. And my final K is less than 1. So if K is less than 1, we've done this enough, it's going backwards still to the reactants. And then you look at your equation to see what's on your reactant side. There's one of these on the study set. There's also a KF. This is not a KF. So I'm going to segue for a minute and mention KF because the KF shows up on your worksheet. KF stands for formation of a complex. So in that case, you're doing the cation plus the ligands, and you're going to the complex. The complex is on the product side because you're forming it. And actually, if you look at the chart, those charts for Ksp or for Kf, which, here we go. Really miss my huge lab bench that's always in front of me. So it shows you that you're forming the complex, and they're called complex ions because they're always made up. These are the ligands, so it's the cation, and these are always positive values. So it's different from Ksp. Kind of keep that in mind. All right, let's keep moving. All right, barium sulfate. Doesn't give me anything else, just gives me lots of information about when you get a barium enema. And right, that's how they're gonna take a picture. It's not radioactive, it actually fluoresces, which is pretty cool. And just the 1-to-1 ratio. And it says you add this amount. It doesn't say this is how much is dissolved. You can't do anything with that mass. So we solve for X. We know the Ksp. So be careful of the wording. That was the question on that worksheet 7. The mass, we can't do anything. We will because we're going to solve for precipitate. So you're just doing the Ksp equals X squared. Solve for X, which will be in moles per liter. And then you're going to go to grams. So I'm going to pause this, give you guys a few moments to try that. And if you want, you can try the next one too. All right, let's do this. Oh, your teacher didn't figure out that number. So you'll get a number here, right? You'll just take the square root of the Ksp. And that is moles per 1 liter. If it helps you, put that 1 there. We want to change moles to grams. It is, everything's 1-to-1. So if you see that and you want to just, we're going to go to of the barium sulfate of the whole compound. If it's not a 1-to-1 ratio, you want to be careful. So we should technically show the mole to mole that this is 1 mole of barium to 1 mole of barium sulfate, but everything's 1-to-1. So we want the mass of the whole barium, sulfur, and 4 oxygens, but we do need to factor in the volume. So we're going to multiply by the 0.75 liters. There's nothing down here. You can draw your unicorn or whatever you do. That gives you a mass. This is the grams that dissolve. Whenever you solve for X, X is telling you the mass that dissolves. How much is aqueous? So the last step, and I just realized I had never punched it in. I was sitting staring at my cat clock. We do go back. The only time we'll use that, well, in this case, if I ask you how much precipitates, that 1.234 grams is the total mass or the initial mass. So I talked about this yesterday. There's 2 parts, right? So we have our test tube this goes with my note to myself. So lab 5 is the titration lab. That's all calculations. The last 3 labs are special. They're all the same theme. So lab 6 is what's going to be due Tuesday, and there's a video you're going to have to watch that will go through this. And so it's very different from any lab we've done, like the whole year. But it goes with this Ksp stuff. And then 7 and 8 are the same theme. They're just different ions. That you have a precipitate, which is the solid, or PPT. And then up here in the solution are the ions. So this is what dissolves. So this is also called the supernatant. So in the video, I talk about that. The supernatant is what dissolves, and the precipitate is what precipitates. The total is the total of the two. So we dump this in there. Most of it's going to precipitate, but whatever this amount is that you get is the amount that dissolved. And again, I'm sorry, I didn't do my math. I grabbed the wrong sheet. And you subtract, and the mass you get, which apparently is not much different, is the precipitate. You're not going to change your metric unit. You just keep it in grams. And this went to 3, so that goes to 3. So the amount that dissolves is always a really tiny amount. All right. On the next one, all we have is aluminum hydroxide. And aluminum is one of our 3s. Not many things have a 3, but aluminum has a +3. Also, if you see a Roman numeral 3, so on the worksheet 7, there was a chromium with a Roman numeral 3. That was a +3. So there were 3 hydroxides in that problem. So that was, I think, the second question on the worksheet. All right, that's all I know. So this is X and this is 3X. Because there's no other information. We haven't mixed 2 things together. There's no KOH. So on the worksheet, this is like 2A, and then 2B, suddenly we knew the hydroxide, so we didn't triple it. We write our Ksp. The other comment I was going to make, the lab 6 is due Tuesday. You can wait until after the exam to worry about it, but I will post it Saturday. So if you're somebody who your weekends, you like to get things done, you can do that. That's the only thing that's going to be due Tuesday. So you should be able to do it, no problem. All right. This is X, and then the 3 and the X are cubed. This is not 9. This is 3 cubed, which is 3 times 3 times 3, which again is not 9. Done this enough that people do 9. It is 27. And then there are 3 X's here, and there's another X there. So this is actually 27 X to the 4th is going to be equal to our Ksp. So just to walk through the algebra real briefly, you can solve. I don't need to know every time you solved with your TI, whatever. I will just know I need to see this. You can tell me X, but I want to walk through how to solve because there were a couple people who did some funky stuff on their worksheet. You are going to divide by the 27. And then to get rid of that 4, you have to do the opposite, which means you go to the 1/4 power of that. So just be careful or take time. It often only takes a couple moments in an office hour or right before or after class. All right, you get X. X will be, oh, I actually did this one. 2.90 e to -9 moles per liter. And assume I did this one apparently last year. and then moles to grams of the whole compound. So that's going to be around 78-ish grams per mole of the aluminum hydroxide. I should have done a mole to mole ratio, and I'm going to do it underneath here. That this is X, that is my aluminum. So technically that's my aluminum. It is not the hydroxide, because hydroxide is 3X. So you'd have to triple that number to have that. And it is a 1 mole to aluminum hydroxide. Right, and then I did give you a volume, so 3.14159 pi liters, and we get a mass. So you're going to get 7.1 times 10 to the negative 7 grams. And then it would have probably said, because it was something that showed up on the one worksheet, it might show up again. We'll probably see it. It will say, report your answer to the appropriate metric. And it was actually fascinating looking at the worksheets, because the students who had me used all the different metric units. And some of you, I don't know, did you, hopefully you learned metric. I know you did. So the metric unit is more than just milli and micro. It keeps going. Google it, print out a thing of it. In this case, we will go to micro, because micro means 10 to negative 6. So you can show that 1 microgram is 10 to negative 6 grams. But after micro comes nano, so 10 to negative 9. And then pico is 10 to negative 12, and then femto, and then I think it's the A and atto. It keeps going. They change by 1,000, by 3s, which is actually quite fascinating for metric in both directions. All right, being comfortable with the metric system, you'll be thankful when you take physics and other things. Probably won't realize you're thankful, but you will be. And again, lab 5 is all titration stuff. And Monday is a celebration, and then we move on to new stuff. So the only thing that we do Tuesday is qualitative analysis. So you'll get to watch a video of me doing stuff in lab, and it's a different lab than we've done. I will see you Friday office hours, and yeah, all right.